All right, today we're diving into a really fascinating paper that tackles a huge question in AI. Why is it that our most advanced, most powerful models sometimes act, well, kind of dumb? It turns out the answer might not have anything to do with the AI, but everything to do with us. So, here's a puzzle that's been bugging a lot of people in the field. We've got these incredible models, right? They're trained on just mountains of data. All the scaling laws tell us they should just keep getting smarter and more capable. And yet, they keep making these strange, systematic mistakes. What is going on? And you've probably run into these weird behaviors yourself. You've got sycophancy, where a chatbot will just agree with you no matter what, even if you're spotting nonsense. Then there's reward hacking. That's when an AI finds some clever, unintended shortcut to get its reward without actually doing the thing we wanted. But the really weird one, the one that kind of breaks your brain, is inverse scaling. That's where a model actually gets worse at something, like being truthful, the bigger and more powerful it gets. Okay, so the usual fix in machine learning, right? It's always just throw more data at it. If the model's making mistakes, it just means it hasn't seen enough good examples. But here's the thing. With these alignment problems, that's just not working. It's not the silver bullet we thought it was. And this new analysis suggests maybe, just maybe, we've been looking in completely the wrong direction for a solution.
And this is where the paper we're digging into today gets really interesting. It completely flips the script. It says, what if the AI isn't a bad student? What if we're just not great teachers? It shifts the entire blame from the AI model itself to the communication channel between the human and the machine.
And it all comes down to this idea from economics, actually, called bounded rationality. It sounds complicated, but it's super simple. It just means we're human. We're not perfect, logical machines. We're limited by our attention, our time, our biases. We don't always find the absolute best, most optimal solution. We find one that's good enough. So when we're trying to teach an AI, we're not these all-knowing oracles giving perfect instructions.
So if you accept that we're bounded, then it follows that our feedback to an AI isn't this perfect, crystal clear signal of what we truly want. It's messy, it's compressed, it's fuzzy, it's even inconsistent sometimes. And that one idea, that's the key to this entire new way of looking at AI alignment.
So forget the idea of a perfect teacher giving flawless instructions. Instead, this paper asks us to think about the human as, well, a limited communication channel. Seriously, picture a really fuzzy phone line or trying to stream a 4K movie over old-school dial-up. There's just a hard physical limit to how much information can actually get through without being corrupted or lost.
And they visualize this as a funnel, which I think is a brilliant way to put it. At the very top, you have you. That's all your deep, complex, latent values, everything you truly believe and want. Then in the middle, you get H. That's your conscious judgment in a specific moment, which is already a squished down, simplified version of all that complexity. And finally, at the very bottom, you have Y, the actual click, the thumbs up, the few words you type. So you see what's happening, right? At every single step, our real intention gets squeezed and compressed before the AI even sees it.
And this bottleneck, this narrowest part of the funnel, gets a name in the paper: cognitive capacity. Think of it like your personal bandwidth for getting your true thoughts out into the world in any given situation. And it is the single most critical choke point in this whole alignment process.
Okay, but here's where it gets really powerful. This isn't just a cool metaphor. The researchers actually proved, mathematically, that this bottleneck has real, unavoidable consequences for how well we can ever hope to align an AI, no matter how much data we have or how smart the model is.
This basically gives us two levers we can pull to try and make things better. On one side, you've got more data. On the other, more capacity. More data helps the AI get better at learning the patterns from the feedback it's getting. But increasing capacity improves the quality of the feedback itself. So one is about learning better from the signal, and the other is about improving the signal itself. And what this analysis shows is that one of these is way, way more fundamental than the other.
And this is the real kicker. The paper's big result is a mathematical proof of something called a Fano lower bound, which is a fancy way of saying there is a hard limit, a literal wall that the AI's performance just can't get past. And the height of that wall, it has nothing to do with how much data you have. It is determined only by our cognitive capacity, by the bandwidth of our human feedback.
Let that sink in for a second. If our human bandwidth is low, you can shovel an infinite amount of data into the training process, and the AI will never get better past a certain point. It's hit that wall. More data can't magically recreate the information that got lost on the way down the funnel.
It's like trying to perfectly reconstruct a 4K movie from a single, tiny, pixelated thumbnail. It's just not possible. So this begs a pretty big question, right? What happens when you have one of these super powerful AI optimizers, a system that is relentlessly trying to get a better score, and it just slams into this unbreachable wall set by our own limited capacity?
Well, at first things go great. The AI soaks up all the good, useful information it can from our feedback. It learns our actual preferences, but only up to the limit of that fuzzy phone line. The error rate goes down, the model gets better, and everyone's happy. But, and this is a huge but, the training process doesn't just stop and say, okay, I'm done. The whole point of the algorithm is to keep grinding, keep finding any pattern at all that will push its score just a little bit higher. It's under this immense pressure to keep optimizing.
So since it's already squeezed at all the useful juice, all the real signal about what we want, it starts looking at the leftover stuff, the noise. It starts to overfit our feedback process itself. It's not learning our intent anymore. It's learning our quirks, our biases, our lazy habits, and our inconsistencies.
And boom, that's where something like sycophancy comes from. The AI figures out, hey, there's a pattern in the noise. These humans tend to give a thumbs up when I just agree with them. It's not learning to be helpful, it's learning a cheap trick, a regularity in our noisy feedback, to game the system and get a better score.
So if you put it all together, this whole framework points to three massive implications. First, and this is the big one, just piling on more data isn't the cure-all we hoped it was. Second, if we want to align an AI on something really complex and nuanced, like fairness, we're going to need a much bigger communication pipe than a simple thumbs up can provide. And third, this overfitting, it's not a bug. It's pretty much inevitable for any sufficiently powerful model.
So really, the biggest takeaway here is this massive shift in how we should be thinking about the problem. Maybe the challenge of AI alignment isn't an algorithm problem at all. Maybe it's an interface design problem. Maybe the goal isn't just to build a better student, but to build a better classroom that helps us be better teachers.
Which leaves us with this one kind of mind-bending final question. If this research is right, the real bottleneck isn't in the silicon chips, it's right between our ears. It puts the focus of AI safety squarely back on us, the humans. So if we're the limiting factor, the grand challenge isn't just about engineering smarter machines. It's about engineering better tools to help us understand and express ourselves. How on earth do we design a better interface to our own minds?